Hi everyone, let's talk about parametrizing all Pythagorean triples. Here's the general problem. Let's say we have a right angle triangle with side lengths A and B, so those are the legs, and the hypotenuse is C. Then the Pythagorean theorem says that a squared plus b squared equals to c squared. And a certain problem that has existed since antiquity, at least since ancient Greece, is to find A, B, and C that are triples of positive integers, so that satisfy this equation. So we want to parametrize all of them, like write them in a way that they generate all possible solutions. And there is a way of doing it. I'll start off with Euclid's formula. Now, Euclid's formula is the following triple: m squared minus n squared, 2mn, m squared plus n squared, for integers m greater than n, and n is greater than 0, so they're positive. What we can check is that m squared minus n squared plus 2mn squared is equal to m to the 4 minus 2m squared n squared plus n to the 4 plus 4m squared n squared is equal to m to the 4 plus 2m squared n squared plus n to the 4, and that's equal to m squared plus n squared squared. Okay, so this is in fact a Pythagorean triple for all m and n like this. And note that we need m is greater than n in order for the first term to be positive. Okay, so the question is, does this generate all possible Pythagorean triples, and does it do so in a unique way? And the answer is no, because take a look at this. We have m squared minus n squared, so the first term, plus m squared plus n squared divided by 2 is equal to m squared. So what we need is a plus c over 2 is equal to a square. Now, we have the Pythagorean triple, the standard one, 3, 4, 5, and we can scale it up to get 6, 8, 10. So 6 squared plus 8 squared equals 10 squared. So notice that this one here, this has to be m squared minus n squared if it's possible at all. If we take it as a, and we take 10 squared as c and 8 squared as b, then 6 squared, we need a plus c over 2 to be m squared. 6 plus 10 over 2 is equal to 8, and that is not a square. So this is not parametrized by Euclid's formula. Now, the question is, how can we parametrize all possible Pythagorean triples? What we can do is that we can look at primitive triples. The primitive triples are those triples such that GCD of A, B, and C is equal to 1. In this case, what happens is that like 3, 4, 5 is a primitive triple, but 6, 8, 10 is not a primitive triple since the GCD of that is equal to 2. What we're going to do is, I'm not going to prove this because I've gone through the proof of this characterization a couple of times and it's just brutal. But I'm going to tell you what the characterization is of all primitive triples. The characterization is that, first of all, I'm going to make an observation that if a squared plus b squared equals to c squared, and GCD of A, B, C is equal to 1, then they can't all be even, but if both of these two are even, then this one has to be even as well. So what we get is that we can assume A is odd and B is even. Then what happens is that what we can do is that we can assert the existence of t greater than s greater than 0. These are both integers, such that a, b, c is equal to t squared minus s squared, 2ts, t squared plus s squared. So there's a distinct similarity to Euclid's formula. In fact, it's in the same form. We're just asserting that A is odd and B is even, and we're saying that this is for primitive triples. Now I want to make two observations. First of all, T and S will be coprime, so they will not share any factor other than 1 and negative 1, and they will have opposite parity. So one will be even and the other will be odd. Now in the other direction, what we can say is that if t is greater than s and s is greater than 0 and they're coprime with different parity, then what we have is that A, B, C equal to t squared minus s squared, 2ts, t squared plus s squared. Not only is it a Pythagorean triple, it is a primitive Pythagorean triple. So both directions hold. And just to be clear, in the primitive Pythagorean triple, the second term, B, is the even one out of A and B. So I hope this classification helps you out in Olympiad problems. Thanks for watching, and I'll see you next time.